Hi there, in this video I'm going to configure my PLC station using the hardware configuration window. Also, during a simple project, I'll show you how the accessible nodes icon can be used to see which PLCs are connected to my computer and what the set PGPC interface is in Simatic Manager software. Alright, let's start the video with an empty project. Note that you can click on this icon to create your empty project. Well, let's right-click and add a Simatic 300 station. First, I need to configure my PLC station in Simatic Manager software. So let's double-click on this icon, Hardware, to open the Hardware configuration window. Now, inside the opened window on the right side and from the Simatic 300 list, I can find and add my modules. First, I need a simple rack. As you see, 11 modules can be added to a standard rack. The first row determines the power supply type. Because I'm not using any of these power supplies of Siemens, let me leave the first row. It doesn't affect the programming step. Inside the second row, I have to specify my CPU model. I'm using CPU 315 2DP. Note that the CPU model, version, and also its order number can be found on the CPU. Okay, let's continue. The third row is used to determine the type of interface module. This module is used to extend S700 stations up to 3 racks. Well, I don't have this module, so let me go to the next rows. Note that there should be no empty spaces between the modules. After the third row, I should specify other modules which were installed beside my CPU. There are lots of modules. For example, CP modules are used to transfer the data in a case of not having the required port on the CPU. All function modules are intelligent modules that perform technological tasks such as position determination and other complex functions in the automation independently. My modules belong to the SM category, which is an abbreviation for signal modules. Signal modules are the interface of the CPU to industrial processes. I'm using 2 digital inputs, 1 analog output, then 2 digital outputs, and finally 1 analog input. Now let me find and add these modules to my project. Alright, I added my signal modules. As you see, Semantic Manager has assigned these addresses to my signal modules. Let me explain its rule. For digital input modules using this table, which shows the input image memory structure. My first digital input module supports 16 inputs. In other words, it only needs 2 bytes. Therefore, Simatic Manager has assigned bytes 0 and 1 for the first module. Similarly, my second module needs 2 bytes. PLC has skipped byte 2 and 3 and then used byte 4 and 5 for the second module. Why? Note that digital modules of Siemens support up to 32 digital inputs or outputs. In other words, 4 bytes. Therefore, Semantic Manager has reserved these 2 bytes automatically. Maybe I need to replace the first module with another one later which supports 32 inputs. In this case, I can use these 4 bytes for the new module without changing the other addresses. So for industrial projects, I prefer not to change the default addresses. In this video, let me show you how they can be changed. For example, let's change the default addresses of the 2 digital output modules. Alright, I've defined my hardware. Now let me click on the Save icon. As you see, my CPU has been added to my project. As you know, this block OB1 can be used to write my program. Note that the hardware information must be downloaded as well as the PLC program. So let me open the hardware configuration window and then click on this icon to generate the system data inside my project. The system data includes my configuration settings and can be downloaded to my PLC. Alright, as you know, beside the OB1, I can add other blocks manually. For example, let's add OB100. Now let's open the OB1 block to write a simple program. Okay, remember, based on my settings inside the hardware configuration window, I0.0 and I0.2 refer to the first and third digital inputs on this module. Also, this address Q0.0 refers to the first digital output on this module. Alright, the performance of this program is similar to this electrical circuit. Let me test it. Okay, now let's test the PLC program. First, I need to run the PLCSIM simulator, where I can click on MRES to reset the virtual PLC. Also, let me select this item, always on time. Now I can select OB1, OB100, and also the system data, and then click here to download them one by one. Or select the Simatic 300 station and then click on this icon to download all configuration settings and program codes. Okay, now let me test my PLC program using the simulator like the previous video. Alright, let's exit from the online mode. Note that every time I can click on this icon to see which PLCs are connected to my computer. Now, this virtual PLC is connected to my PLC via its MPI port. Let me close it and test my connections again. Well, as you see, there isn't any connection. Let me connect my PLC to my computer using its MPI port. So I need to open the options menu and select Set PGPC interface. In this window, I can change the connection settings between my computer and PLC. Let's select PC adapter MPI. Because I've connected my computer to the MPI port of my CPU using this cable. Now let me click on this icon. As you see, my PLC is connected to my computer directly using its MPI port. Pay attention. If the PLCSIM simulator is opened, Simatic Manager won't detect my PLC. Let me test it. Okay, as you see, between the virtual CPU and my real PLC, Semantic Manager has detected the virtual CPU. I need to close all virtual CPUs to have a connection with my PLC. Again, let's click on the Accessible Nodes icon. At this time, Semantic Manager has detected my PLC. Now let's download the Simatic 300 station to my PLC. Alright, the project was transferred successfully. Now I can test it. Before that, let me tell you a useful point. If I change my program a little, for example, if I change this input address, I don't need to transfer the whole project again. I can save my program and then click here to transfer only the new program. Now let's test the program using my PLC. Now let's see how symbols or tags can be defined. Also, I'll show you how a project can be uploaded from a PLC. Then I'll explain and test set and reset instructions. Okay, I define a new project, configured my PLC station, and also tested this simple program using the PLCSIM simulator and also my PLC. This program is very short and simple, but an industrial process needs a more complex program with a lot of addresses, which can confuse us to detect each address represents the status of which input or output of the PLC station. In other words, which parameter in the industrial process. So I recommend you to define a suitable symbolic name or tag for each address. It can help us to understand the logic of the complex programs. To define a tag, I can right-click on each address and select this item, Edit Symbols. Now I'm going to use a stop and a start tags for these two inputs. Well, another way to define tags is using the symbol table under the Options menu. Here you can see the defined tags and also add your all tags and then start the programming step. For example, let's define a tag for the output address Q0.out. Okay, as you see, all addresses in my program have a suitable tag. As I mentioned earlier, these tags only help us to understand the program's logic, but my CPU doesn't need them to execute my program. Note that under the View menu, I can determine whether the defined symbols should be displayed or not. Well, as you see, many actions have a shortcut in Simatic Manager. For example, let's use these shortcuts to see the defined symbols in my program again. Okay, let's save the program and close the current window. Well, as you see, there is a symbols icon next to the block folders. I can use that to open the symbols table and define my tags. Alright, my computer is connected to my PLC directly using its MPI port. Let me transfer the current project to my PLC. Note that here is an important point. Simatic Manager transfers only necessary data, such as my program and configuration data. It doesn't transfer the defined tags inside the symbols table. Alright, I've transferred the project to my PLC. Now let's open the PLC menu and then select this option, Upload Station to PG, to transfer the loaded project from the PLC station to my computer. Now let's click on the View button to find my PLC, and then I need to click on OK. Alright, now I have two PLC stations. The second one is uploaded by my PLC on my computer. Let's open its main block, OB1. As you see, the uploaded program doesn't have any symbol. Let's open the symbols table to check this point. As you see, there isn't any tag inside the symbols table. Remember, I configured my PLC station, so if I open the hardware configuration window, you can see that the uploaded project includes the hardware information too. Okay, to have the defined tags inside the symbols table, I recommend you to save your projects on your computer after transferring that to your PLC. Now let's do another test. Let me reset my PLC using its mini switch and then transfer its data to my computer. Alright, here is a new PLC station. Let's open its symbols table. Okay, the symbols table is empty. Now let's open the blog folders. As you can see, there isn't any organization blogs or program. We can see only the system data. So let's open the hardware configuration window. As you see, only the CPU model and the previous addresses are detected. For other modules, I need to double-click on each module and then determine its order number to remove these question signs. Alright, let me exit from the hardware configuration window and delete these two extra PLC stations. I recommend you, before starting any project, first transfer the current data on your PLC to your computer. Also, after finishing your project and transferring that to your PLC, save that on your computer to have all data such as the symbols table. Now let's open the main block OB1 to write and test some simple programs. Okay, as you see, the OB1 block includes one network. I can select the title for that and also write a comment. That's optional. Now let me right click and select this item, Insert Network. Again, I can write a title or comment for the new network. Also, I can click on this icon to have more networks. So, as you see, a program inside the main block can be divided into some networks. On the left side, you can see the instructions that can be used. Now, let me use a SR instruction to rewrite my program inside the first network. This instruction needs a bit of memory to work correctly. SR is an abbreviation of set and reset actions. I can use its first input to turn on an output and use the second one to turn off the output. As you see, instead of writing addresses, I can use the defined tags. Now let's download the program and then test it. Okay, as you see, the performance of the programs inside the two networks are the same. Note that PLCs execute the whole program and then update their outputs. So if I press the start and stop push buttons at the same time, the SR instruction decides to turn on the second output and then decide to turn it off. Therefore, based on the last decision, my PLC turns off the second output. Alright, now let me compare the RS instruction with the SR. Note that the first input of this instruction turns off its output, and the second one enables its output. Okay, now let me save, download, and then test the program. Well, as you can see, the performances of the two networks are the same. But when I press the start and stop push buttons at the same time, the RS instruction turns on the first output, but the SR instruction turns off the second output. Note that you can use the set and reset instructions individually. Let me explain them using the help window. I can click on this question icon and select the reset instruction. Here you can see a description about the reset instruction. This instruction can be used to reset a selected address to 0. Note that if I don't activate this instruction, it won't change the current state of the selected address. At the bottom, you can see some examples of using this instruction. Similarly, let's use the question sign to learn the set instruction. This instruction can be used only to set a specific address to 1. Now I'm going to use only normally open and closed contacts to implement some simple electrical circuits. Also, I'll use them to write a simple program to implement a star-delta starter. It's a common method in industries to reduce the starting current of three-phase motors. Alright, let's start with this program, which was tested already. At the bottom, you can see its equivalent industrial circuits with relays. As you see, it includes a control circuit and a simple power circuit to turn on a three-phase motor. As you may know, PLCs are an alternative to implement industrial control circuits, not power circuits. Now let me tell you an important point. Because I've used normally open push buttons at this PLC wiring diagram, my program is similar to this control circuit. Otherwise, I'll need to modify my program. Let me explain it more. Well, a push button can be normally open or closed, and a contact in a program can be normally open or closed as well. So there are 4 states according to the type of push buttons and contacts. At the first line, the contact and also its related push button are normally open. Let's review how the CPU executes the first line. In normal conditions, the 24 volts doesn't reach the first digital input terminal. So the CPU doesn't change the state of the first contact at the first line. In consequence, the virtual power can't reach the first digital output. So the first digital output is off in normal conditions. But if I press the first push button, the 24 volts reaches the first digital input terminal. So the CPU changed the state of the first contact from open to closed. Now the virtual power can enable the Q0.0 address. So if I press the first push button, my CPU turns on the first digital output. The important point is that the state of this contact is changed based on the state of its digital input address, which works based on the voltage level at its input terminal, not based on the type of push button. Now let me explain the last line, which uses a normally closed push button and a normally closed contact. In normal conditions, the 24 volts reaches the last digital input terminal. So the CPU changes the state of this contact from closed to open. So the virtual power can't enable the digital output, and like the first line, this output will be off in normal conditions. But if I press the last normally closed push button, the 24 volts doesn't appear at the input terminal. So the CPU doesn't change the state of this normally closed contact. In consequence, the virtual power can reach the fourth digital output and turn it on. As you saw, the performances of the first line and the last line of my program are similar together. Similarly, the performances of the middle lines are the same. In normal conditions, these two outputs are on. When I press these two push buttons, the CPU turns off these two digital outputs. Note that these two lines of my program are different, but their overall performances are the same because of using a different type of push buttons. Now let's do a more complex project to learn a simple way of PLC programming. First, pay attention to this industrial circuit. As you can see, there are three conditions that can turn on the lamp. Also, three conditions can activate the K1 contactor and in consequence the three-phase motor using the power circuit. Well, I can use an input-output module with this wiring diagram to implement the control circuit using a PLC station. Note that if normally open push buttons are used, the program inside the CPU will be similar to its equivalent electrical circuit. Also, two digital outputs are used respectively for the lamp and the K1 contactor that can turn on the three-phase motor. Well, these three states of the circuit illustrate the all conditions that the lamp can be on. Similarly, the CPU can use this program to turn on the lamp. A simple program in ladder language has three parts: the virtual power on the left side and some conditions that can turn on an output. Now each line of my program is written based on one condition that can turn on the lamp. Similarly, there are three conditions to turn on the three-phase motor. So I can use this program to control the lamp and the three-phase motor with my PLC station instead of this electrical control circuit. Note that I can change the PLC program easily without changing its wiring. This is the most significant advantage of using PLCs. Before implementing the next industrial circuit, I should say I'm using normally open push buttons like this diagram. If you use normally closed push buttons at your PLC wiring diagram, you may need to change the type of the related contacts inside the program. Alright, this is a star delta starter. It's the most commonly used method for the starting of a three-phase induction motor in industries. In this circuit, the induction motor is connected in through a star connection during the starting period. Then, once the motor reaches the required speed, the motor is connected in through a delta connection. In this diagram, there are three push buttons to stop the motor, start the motor with its star connection, and a push button to switch the motor to its delta connection. This control circuit uses these three contactors to control the motor. You can use the ECRTS software to simulate and learn this circuit. Now let's write its program in Simatic Manager software. I wanna write a program to control these three contactors, power, star, and delta. I configured my PLC station, so let me open the main block, OB1. Now let me add a suitable title and comment to my program. Alright, let's add a network. As you saw, the power contactor should be enabled with the start push button and disabled with the stop push button. So I can use ASR instruction easily for that. Okay, the second contactor, star, should be on when the first contactor is enabled. Okay, I need another network for the delta contactor. When I press the third push button, this contactor should be enabled. Naturally, when the stop push button is pressed, the delta contactor must be disabled. Now let's add an important safety condition. According to the power circuit, the star and delta contactors must not be enabled at the same time. So let me use a normally closed contact of the third digital input here. In consequence, when I press the third push button, the star contactor will be off. Also, when the delta contactor is enabled, the star contactor must not be on. So let's use a normally closed contact of the third digital output before the second digital output, which enables the star contactor. Now let's add similar safety conditions to the third network. When I enable the third digital input to enable the delta contactor, the first contactor must be on and also the star contactor must be off. Alright, this is a simple program to implement the star delta starter with AS7300 PLC. Now let's test it with the PLCSIM simulator. Okay, let's use the second digital input to enable these two digital outputs. Well, to see the state of the contactors, I need to modify this address on the PLCSIM simulator window. As I mentioned before, I can change the program logic without any changes in the PLC wiring. For example, let's use a negative pulse detection after the start contact. Therefore, the three-phase motor will be started when I press and release the start push button. Now, let me test the new program. As you can see, I need to enable and also disable the start contact to activate the two first digital outputs. Similarly, I can test the program using my PLC station. I need to close the PLCSIM simulator and then download the program into my CPU, which were explained in the previous videos. Alright, I tested some simple electrical circuit using the EKTS software and then explain how they can be implemented by AS7300 PLC. Now we're going to learn the instructions that can be used to detect positive or negative edges. After that, I'll show you how the factory I/O software can be used during this course. That's a great software that can connect to different bands of PLCs and simulate industrial processes. Okay, I configured my Simatic 300 station, so let's open the main block OB1. I'm going to explain and test these instructions that are used to detect positive or negative edges. Let's learn them with these two instructions. Well, this instruction needs a bit of memory to work correctly. This instruction checks any change in the state of the RLO behind itself. If the state of the RLO behind the instruction changes from 0 to 1, the output of this instruction will be on only during one scan cycle. In other words, if you consider the left line as your virtual power line, when the virtual power behind the contact changes from the off state to on, the output of this instruction will be on only during the next scan cycle. Now let's use this instruction. Similarly, it needs a bit of memory to work correctly. This instruction detects positive edges in a specific address, which should be entered here. For example, let's enter the first digital input address, I0.0. Now, this instruction compares the signal state of the first digital input with the signal state from its previous scan cycle, which is stored in M0.1. So, if this instruction is enabled and the state of the first digital input changes from off to on, the output of this instruction will be on only during the next scan cycle. Now let's save the program. As you see, Simatic Manager has detected an error. It says a preceding logic operation is necessary because of connecting this instruction to the left line directly. In consequence, the state of the RLO behind the first instruction is always on. Let me use a normally open contact behind it with the first digital input address. Now, the performances of these two instructions are the same. Again, let's save the program and test it using the PLCSIM simulator. Okay, as you see, when I enable the first digital input to generate positive signal edges, you can't see any changes in the state of these two digital outputs because my program is executing continually and one scan cycle takes a very short time. I need to enable the single scan option to see how my program is working. Again, let's enable the first digital input. So the state of the I0.0 changes from 0 to 1. In other words, I have a positive signal edge in I0.0. Also, based on the program, the RLO behind the first instruction has changed from 0 to 1. So these two instructions produce a pulse that takes only one scan cycle. For the next scan cycles, the outputs of these two instructions return to 0. Okay, as I mentioned earlier, if the continuous scan option is enabled, maybe we can't see that the outputs are turned on during one scan cycle. Therefore, set and reset calls are usually used to restore positive or negative edges. Okay, let's continue the video with this program. Based on this program, I can use the first digital input to turn on the first digital output and use the second or third digital input to turn off the output. Try to test it. Now let me change it a little using these two instructions, the positive and negative ILO edge detections. Because of some safety reasons, industrial processes are usually started after pressing and also releasing a normally open push button. So let me use the negative oil or edge detection after the first digital input. Also, industrial processes are usually stopped immediately when the related push button is pressed. If I use normally open push buttons for the second and third digital inputs, I need to use the positive oil or edge detection after the next two normally open contacts. Now let's save and test the program using the PLCSIM simulator. As you see, I should enable and then disable the first digital input to turn on the output. But if I press the second and third digital input, the CPU turns off the output immediately. Now, let me test the program using the factory I/O software. It's a great software to simulate simple industrial processes. Well, let's create a new project. Okay, on the right side, I have a list of industrial equipment. Let me design a simple control box to control a warning light. Note that if you want to change the height of an equipment, press the V key on your keyboard. Now let me add different types of push buttons and a warning light to the inserted control box. As you see, some inserted equipment have a tag or name. I can use this icon to see or hide the name of actuators, which can be connected to my PLC outputs. Also, the name of sensors or push buttons can be seen by clicking on this icon. This category of equipment can be connected to my PLC inputs. Now I wanna connect these three push buttons and the warning light to these digital input addresses and the first digital output respectively. First, let's define a suitable tag for each address in my program. That's optional. Okay, to make a connection between the factory I/O software and my PLC, I need to select the drivers option under the file menu. Now I need to select my PLC type. If you are using a real S7 200, 300 or 400 PLC station which supports an Ethernet port, you should select this item. Then go to the configuration section, select your PLC station, and enter the IP address of your PLC station. Now my PLC station doesn't have any Ethernet module. Therefore, I want to use the PLCSIM simulator. So I need to select the last item, Siemens S7 PLCSIM. Then I need to select its version, determine my numerical data type, then determine the number of my digital or analog inputs or outputs. For the current project, I need 3 digital inputs and 1 digital output starting from the first byte 0. Now I only need to click here to connect the factory I/O software to my PLCSIM simulator. Here you can see the selected addresses which are used in my program too. Now let's connect them to the inserted equipment inside the factory I/O software. Okay, I set up the necessary connection settings. Now let me enable my virtual PLC. As you see, the third digital input has enabled immediately because the stop push button is normally closed. Now let me sort the windows to have a better view of my program, the PLCSIM window, and the designed control box inside the factory I/O software. Okay, let's test the program. As you see, I need to press and release the start push button to turn on the warning light. If I press the reset push button, my virtual PLC turns off the warning light immediately. But if I press the stop push button, the warning light isn't stopped immediately. I also need to release this push button because the stop push button is normally closed. To solve this problem, I need to replace the stop push button with a normally open push button. But this way is not recommended. Because of safety reasons, the type of emergency and stop push buttons are normally closed. It's better to modify the program. I can replace the positive RLO edge detection with a negative type or change the normally open contact with its normally closed contact. Again, let's save, download, and test this program. Okay, until now, we have learned important bit logic instructions and also different ways to test a program. I can use a real PLC station or the PLCSIM simulator and also connect them to factory I/O software. In the next videos, I'll prefer to use the PLCSIM simulator with factory I/O software to simulate and test my programs. Thanks so much for watching this video.